Okay, good morning, everyone. Very happy to see you. Today is a raining day, so I think some students are still in the way to go to this classroom. However, we may need to start our class, and actually, this is the last week before the final examination of our course. So today, I will, as usual, to try to give you some questions for review about what we have learned in the last week. And as you may remember, in the last week, we have already talked about some specific examples and design ideas of the fault tolerance design. And in the last week, our focus is on hardware redundancy-based methods. So we introduced the static, dynamic redundancy-based method. For example, the TMR, triple module redundancy. So I hope that these examples can give you more specific, concrete ideas about how we can use hardware redundancy-based methods to implement the fault tolerance systems. And today we will again use similar ways to let you know more specific ideas and examples of different redundancy-based methods, including time-based redundancy and also the information redundancy methods. So later we will do that, and before that we will first again have a Kahoot review. So you can take this opportunity to discuss with your team members and also try to challenge yourself to see if you still remember and understand the ideas of these methods. Right. Okay, so before that, I would like to remind you two things for you. The first one is that for our final examination, please remember to check our course website about the time and the locations, and remember that for our final examination, similar to our midterm examination, we have 2 classrooms for final examinations. So please do remember to check our website to see in which classroom you are located to join the final examinations. And also some detailed information about the final examination. And the second one thing is that if you are interested in fill in the teaching performance evaluation form and to get the some bonus points for the semester grades, you still have time to do that. And please check our course website for some information about after you fill in the teaching performance evaluation, you can go to the other Google form to let us know you have already completed that, so that we can register your attendance about the teaching performance evaluation. So once again, thank you very much for this semester in this classroom for this course. So it is really a great pleasure to be here with you. Okay. And now let's have the Kahoot review for the some concept and the examples we have already introduced in the last week. So later you can check the questions and try to find the answers. And as usual, we will try to let you take this opportunity to as a warm up. So we will again ask you some questions. Okay, so is every team ready now? Okay, so let's start our Kahoot today. Okay, so very good. The first key concept in our last week is maintainability. So please try to check if you know maintainability and still remember there are several vectors that can affect the maintainability. So for example, it is quite related to the time that you try to locate where is the reason of the error and then try to repair the errors. So if you still remember, we have some passive time for the engineer to go to your place, and then some active time to locate your failure and try to replace or fix the problems. So about this maintainability, it is also a key attribute for reliability. So when you review for maintainabilities, please try to check if you understand these concepts, okay? And if I ask you in the final examination, please give a formal definition of maintainability. So you can write the probability that a failed system can be restored to operation within a specified time. And here, a very important part is that it is basically a probability. So this is very important, and it is somehow similar to the reliability. So when you review the final examination, please also try to compare what is the similarities and the difference between maintainability and reliability. So I think basically they are all probabilities attributes, but there do exist some difference between maintainability and the reliability. So depending on our application, our fault tolerance methods should be chosen in order to achieve high maintainability or higher reliability. So that is very important. If there is some question, how can we select appropriate fault tolerance methods? The answer should be depending on your application. So for some application, we hope to have high maintainability. For some other application, we hope to have high reliabilities. Yeah. So that is for this one. Okay. So this should be easy, just some basic idea to clarify and to remember. Okay, so this question is more technical. Okay, so still the most part of the teams give the correct answer. So for this TMR, you need to know the idea and some limitation of these methods. So here I have a question for you. Do you know the reason why TMR can tolerate one module to be faulty? Why? Or maybe you can discuss with your team members or check the answers for 1 minute. So if I ask you what is the limitation of TMR and what is the reason, so yeah, please check the answers. Yeah, this question may also appear in the final examination. Okay, you have already the answer. Yeah, very great.
Because the TMR, if it had error and in one module outvoted by other two, because there's a majority voter.
Okay. What is the function of majority voter?
Like the AB or BC or AC, like there's, I forget this what structure this.
And then 3 and 1 or the structure of the voter. Yeah.
Okay, yeah, very great. What's the names of you two?
Chen Jinghe and Huang Weixiang.
Let's give a big hand to Jinhe and Wei Xiang. Okay, yeah, very great. Okay, so for the reasons, if you see this question in the final examination, then you need to try to refresh the memory about what is the architecture of the TMR and what is the operational flow. So basically, we have a voter, a majority voter. So we will choose if there are some majority of the results among the 3 copies of the module. So as long as we see the majority of your answers come from at least 2 for 3 copies of the module, then even though we have 141s, the other 2 for 3 ones can still dominate the outputs. So that is very important. That is the idea of TMR. So for this part, TMR is actually not so difficult and actually widely used in fault-tolerant systems. So it is very important for you to at least know what is TMR, its architecture, and also the operational flow. And remember that for TMR, we have actually one drawback. Our MTTF will be shortened. We will have fewer or little MTTF. So please also try to clarify what is the reason. For TMR, its purpose is not to extend the MTTF or the lifetime of our products. Its MTTF actually will be shorter. So what is the reason and what is the advantage that we still try to use TMR? So that is very important for TMR here. Okay. And for this question, maybe if it is possible, I would like to hear some answer explanation from our student in the back of the classroom. Okay, so it is good that most of you still give the correct answer, but equally importantly, you need to know the reasons. So for students in the back row, do you have any answers? Why for this question the answer is false? For students in the back row? Because it is the last time we can hear your opinions and let you get some bonus points. Do you want to say something about the reasons? No? Okay, yeah.
In normal operation, the
Why code spares
the
cannot be helpful for
the code spare is in rest and it don't work, and you need extra time to power it or initialize.
Okay, so basically you said that for code spares it will not be power on initially, so its purpose is not to detect the faults, Then what is the purpose of for code spares?
It's used as a backup.
Yeah, very good. So basically, it is used to replace the original module when the original module is faulty, right? Okay. Yeah. What's your name?
近期
Okay. Let's give Jinxi a very big hand, yeah, for his sharing contribution for this problem. So here, please try to check in our slides what is code spare and what is the purpose of code spares. So in addition to code spares, we also have hard spares. So you may check that if we talk about hard spares, can hard spares be helpful for detecting faults? So that is an interesting question. And if you clarify that, then you may find actually there are different scenarios, applications of these different fault tolerance methods. So you will have a clear idea how we can choose different methods for different applications. Okay, so this is for this question. Okay, so still we have a majority part of this question to get correct answers. So a very short question. What is the full name of MTTR? What is the full name? Do you remember? Yeah, very good. Of MT.
Mean time to repair.
Okay, very great. Your name? Regine. Let's give Regine a very big hand. Yeah, very good. So you can see 4 terminologies. These 4 terminologies are all very important for our final examination. So please make sure you know what is MTTR, MTTF, FIT, and reliability. These are very important terminologies for reliability parts. Okay, so similarly, MTTF means mean time to failure, and FAT is units for MTTF for failure. So yeah, please try to clarify the relationship between these terminologies. Yeah. Okay. So this talks us about the applications scenario of different fault tolerance methods. Okay, for this one we have some variations. So the correct answer should be the static redundancy. Do you remember some example of static redundancy? Some example of static redundancy. Yeah.
The TMR is
TMR. Okay. Triple modular redundancy, right? Okay. So your name?
戴宇谦。
Chen. Let's give Yu Chen a very big hand. Yeah, very great. Maybe in the final examination, I will ask you, for example, to give a example of these static methods and also describe maybe the full name. So remember, for the TMR, the full name is triple modular redundancy. Okay, and the other question is that if we choose dynamic redundancy, what is our purpose? For static redundancy, our purpose is we don't want to interrupt the operation. We just want to mask the faults so that we don't observe the errors. That is for static redundancy. Then how about dynamic redundancy?
Dynamic redundancy can repair and replace the wrong place, but the drawback is that you have to pause the entire system to replace the.
Pinhan, right? Okay, yeah. Let's give Pinhan a very big hand for sharing these thoughts. Yeah. So for dynamic redundancy, the advantage is that we can locate the faulty components and then try to repair that. But the cost, so you know everything comes with a cost. If you want to do that, then you need to pay some additional time. So this will degrade the performance. So maybe in the future, if you are interested in this issue, maybe your research topic is try to reduce the cost to do that. So that's a possible, very hard research topic. If you have the opportunity to see some papers or to attend some international symposiums, then you will find reducing cost is always a very important issue that we need to solve. Okay, so here, similarly, for these 4 possible methods, you need to know their differences and also importantly, what is the applications and the scenarios of these methods. Okay, so very great for everyone. Try to ask you these questions when you prepare the final examinations. So some example, dynamic. Okay, yeah, it's happy to see that you know the answer is duplicate and compare with hard spares. So actually, if you try to screen the whole 4 answers, you will find that this one, TMR, majority voting, NMR, all belongs to static redundancy. So for this question, this should be the correct answer. However, ask yourself, can you explain the ideas of duplicates and compare with hard spares? What is the architecture and the operational flow of this one? So that is very important. Okay, you need to know the reason why we call this one example of dynamic redundancy. So basically, for this one, we can know which component is faulty, and then we can try to reconfigure our system to make sure our system can still have normal operations. Yeah. Okay. So for the final examinations, I think the key part is ideas of the fault tolerance methods, and can you give some example and try to use that example to explain the ideas. So that is for this one. Okay. Okay, so here comes our final question, an ordering problem. It is about the steps for dynamic redundancy. Okay, yeah, very great. Most of the teams, after your discussion, you find the correct answer. So for dynamic redundancy, a logical flow should be like this one. The first of all, we need to detect in the fault. We need to know if we have errors in our systems, and then try to locate where the errors come from. So locate the faulty hardware, then we reconfigure the system, finally continue operation using the spare ones. So you can follow this order to find the examples we discussed in the slides. Try to map the operations into the examples to see if you can correlate this operation with our examples. So maybe, for example, in the final examination, I will ask you to explain the operations of, for example, the hard spares reconfiguration methods. So you need to use that example to illustrate how can that architecture detecting the faults, locating the fault hardware to do some repair or reconfigurations. Okay, so basically the flow should be like this one, but I would encourage you to when you prepare for the final examination, try to find more specific information about how can we implement these different methods for the examples we discussed in our slides. Okay, so that is also important. Try to do that when you prepare for the final examinations. So I think for the final examinations, it is not so difficult. So I think one good way is that if you find your ways to prepare for midterm examination give you a very high sense of achievement. You also see good grades for your midterm examination. You can use the same way to prepare for the final examination. Yeah, so that is for this one. Yeah. Okay, so this is our last review of our course contents before the final examination. I think you can also use these ways to challenge yourself with some questions to prepare for the final examination. So I think you can easily find that there are many AI tools that can serve as this purpose. You can ask AI tools to ask you some questions to see if you understand the key concept of our slides. So please try to do that. Then I think you can prepare for the final examination more efficiently. Okay, so now let's go back to our new content. For our new content, it belongs to this part. As you can see in the screen, it is for this one, designs of fault-tolerant systems. So for this part, we talk about specific ideas and examples of the different types of the fault tolerance methods. So here, the key part is the idea, the operational flow, and some example architecture. Okay, so remember that we have these three types of the redundancy methods: hardware, time, and the information. And also remember their basic ideas. In this part, we will keep introducing some example to let you know more specifically how can we implement these different methods. Okay, so in the last week, we talked about hybrid redundancy methods. Basically, they combine static and dynamic redundancy. For these methods, we can, at one hand, to mask faults like static. On the other hand, we can also detect and reconfigure our systems. So you can see we have more functionalities. So maybe we can use this way to further increase the reliability or even maintainability of our system. But don't forget, we need to pay more costs. So maybe in the future you can think about if it is possible that we can reduce the cost. But for our course, your focus can be how this concept can be implemented by some examples. One example is this one, TMR with spares. So when you prepare for the final examinations, ask yourself, how TMR with spares can achieve these two goals. So this is one example we discussed in the last week. The other one example is this one, self-purging redundancy. This is also an representative method for hybrid redundancy. And here purging means 净化. So it is 净化 just like you purify your waters. Okay, so it is basically an automatic scheme that can automatically mask our errors and try to reconfigure our systems. So later you will find that its idea, its key part is this one, threshold voter. So later please pay attention to this one to see how this threshold voter help to implement the hybrid redundancy methods. Okay, so here you can see the functionalities of this threshold voter. It will output 1 if the number of inputs are 1 greater than the threshold. So basically, this thresholder is trying to check how many components can generate correct outputs. Okay, so this is the threshold voter. And for this method, it is not using majority voter. It is a threshold voter. So you can see we can specify how many outputs we see that are consistent. Then we determine this output is the correct outputs. Okay, this is the example of this architecture. Assume that we have 5 identical modules. So this is our target module. We create 4 additional the same modules. So here we have 5 the same identical modules. For example, this is an adder, 5 identical adders. And here, pay attention to one specific component for this one. Elementary switch. You can see that we put an elementary switch to deal with, to process the output of every module. And here you can see the architecture of this elementary switch. Basically, you can see that the key part for this elementary switch is actually this one. This is an exclusive OR gate. Focusing on this one, this is an exclusive OR gate. Here we put an exclusive OR gate to compare the voter output with the current outputs. Okay, so basically this is a comparator. We try to compare that because we have a threshold voter here. Remember that the functionality of this one is to check for among these 5 modules, can we find at least 2 modules of these 5 modules can generate correct results. So if the more than 2 modules can generate the same result, we think this answer should be the good answer, the correct answer. So this answer will go back to every elementary switch used to check. So to check if this module is faulty, if this module is faulty. So this threshold voter is used to generate the golden correct result. When you see golden, it means that the correct results. So this is the golden results. Golden result will go to every elementary switch. Basically, it is this path. We will compare this golden correct result to see if there are any difference between correct result and this module's outputs. If yes, if the answer is totally yes, then we will, the output of this one will be logic 1. It means that we don't activate the reset functionality of this flip-flop. So remember that for this reset, it will be activated if we find any differences between these 2. Okay, so the idea is very simple. If we find there are some difference of your outputs with the golden result, then we turn off your module. How can we turn off the module? We activate reset so that this will be a 0 here. This is an AND gate. If we have 0, then this one will be always 0. So the functionality is switching off. Okay, so basically for this one, we use this elementary switch to reconfigure our systems. So here we can try to classify. For every module, we go to this path and use this threshold volter to do the error masking functionality. And then we again use threshold volter to generate correct results, the golden results. And we use this elementary switch to compare if there are any difference between these golden results and the module outputs. So we can use this elementary switch to locate where is the faulty module. And based on the comparison results, we can switch off, we can turn off this module. This is one reconfiguration operation. So this one is responsible for locating faulty components and reconfiguration. And the volter is do the masking part and generating the golden results. Okay, so this is this one. So you can see that actually this architecture should be very easy. So it is published and used in many applications. Self-purging redundancy. Okay, so when you review for this part, try to understand why we have this architecture and what is the responsibility of this elementary switch and this threshold volter. And here you can actually find an interesting problem or question. For this threshold volter, actually you can specify these values. You can arbitrarily determine which value you want. You can have 2, you can also have 3, depending on how many correct results you think are confident to generate the golden results. Here you can see some comparisons. Since here we have 5 modules, actually it is quite similar to 5MR. 5MR means that we know TMR, it is the number of modules is 3. So for 5MR, we have 5 modules, but for 5MR, for this one, remember that the architecture of this one should be a majority volter. And for 5MR, we don't have this elementary switch. For 5MR, our purpose is only to mask errors. But for 5MR, we can tolerate here with 2 spares. So here, try to compare that. For 5MR, we can tolerate 2 spares. Okay, but for self-purging, with the same number of modules, we can tolerate up to 3 failing modules. So you can see that even if we have 3 modules are faulty, as long as we have the other 2 modules are still good, these 2 can contribute correct results. And we can use this correct result to switch off these 3 modules. So because for this threshold volter, this number is 2, so this number actually determines how many modules that you can tolerate to be faulty. So here, focusing on that, for this one, for self-purging with 5 modules, it tolerates up to 3 failing modules. 5MR cannot do that. 5MR can only tolerate up to 2 failing modules. And this one is one limitation of this self-purging with 5 modules. It cannot tolerate 2 modules simultaneously failing. So here the keyword is simultaneously. It means at the same time. So for this self-purging methods, you can see that because its threshold volter requires, its function is to find if any 2 number of the inputs that are also 1. So there is one drawback. How about the situation that the correct answer should be 0? However, these 2 faulty modules, we assume these 2 are faulty. They generate the faulty output, and the faulty outputs somehow happen to be logic 1 at the same time. So you can see that if these two modules generate 40 results and their results are all logic 1, then this logic 1 will be used as the golden outputs. So that is the drawback. For this mechanism, we assume the 40 modules output should be different. However, if this, for example, these two 40 modules generate the same results, but they are 40, then this 40 module, when they go to this threshold voltage, it will be used as a golden result. Then this 40 result will use to switch off these 3 good modules. So that is the biggest drawback of this one. It cannot tolerate 2 modules simultaneously. You can take some notes at the same time, fill in, and try to take some notes to help you understand that. But for 5MR, it can, because it is a majority voter. As long as the other 3 good modules generate the correct result, the other 3 modules is still the majority. Okay, so this is for this one. And we can also compare TMR with 2 spares for this one. For this TMR with 2 spares, it is a dynamic one. If you still remember TMR with 2 spares, if we find some failing modules, then we can use these 2 spares to fix the system. So compared to self-purging with 5 modules, for this one, it is, when we compare to this one, TMR with 2 spares has simpler reconfiguration circuitry. So try to compare this one. If you go back to our slide for this one, we only have the voter. We don't have this one. So its cost is lower, but it requires hot spares. Okay. No, I'm wrong. I'm sorry. These two should be self-purging with 5 modules. For self-purging with 5 modules, they must need hot spares. For these 5 modules, if we say these 2 are our modules and these 3 are 3 spare modules, then all the 5 modules need to be hot because they need to use to detect the faults. However, for TMR with 2 spares, these 2 spares can be cold. Okay, so this is for this one. And for self-purging with 5 modules, its reconfiguration circuitry is simpler. We just use this elementary switch. But for TMR with 2 spares, we will need to switch to use the cold spares, and we also need to have some mechanism to power on cold spares. So our reconfiguration circuitry will be more complex than this one. So this simpler means this self-purging with 5 modules is easier to reconfigure our system. Okay, but of course for this one, we need to have some elementary switch, so the cost will be higher. Okay, so this is for self-purging redundancy. Okay, so when you prepare for the final examinations, or in the future you learn some new design methods, try to compare your new learning technologies with the previous one you have already learned. So for example here, compare with 5MR, TMR with 2 spares, you can find this one, they all have 5 modules. So it is worthy to compare it, for these methods. Do they have similarities or do they have differences? Okay, so this is for self-purging redundancy. So here an interesting question. You can think about that when you review the contents. You can try to challenge yourself. So far, we have learned several different hardware redundancy-based methods. When should we use which one? And how about the cost? So these are very important questions. Okay, so ask yourself these questions when you learn and review for these parts. So this is hardware redundancy based methods. Now let's move on to the second types of the method. It is time redundancy. So remember that for time redundancy, the idea is that we don't want so much high hardware cost. We just want to retry the operations. Maybe the errors comes from some temporary faults. So maybe if I try another time, then the error behavior will be disappearing. So the advantage is this hardware, but the drawback is it cannot detect permanent faults. Okay, so if errors are detected, then usually we will do rollback to non-good states. So for example, if you find there are some errors, we try another time and to see if the errors can disappear. And if we still find there are errors, then we need to roll back. We need to go back to some checkpoints that you saved in order to resume normal operations. This idea is quite similar to your operation systems of the Windows or Mac. When you use the operation systems, you can manually store some checkpoints of your PC. So for example, today you find your PC is in good health, so you store the states of your PC as a checkpoint. So maybe tomorrow you find your PC cannot run correctly. So tomorrow you will do this rollback to go back to the good stats you stored today. So it is the same. It is this idea. We need more time to record your good states and then use more time to detect the errors and resume. So for these methods, the key part is time. So keep this in your mind. Later we will see how we can use some specific technique to implement these time redundancy methods. So later you will see that put the focus on how the errors are detected and the circuit or system design methods. Okay, so let's stop here for 10 minutes break. Then we will talk about some specific examples of this one. Okay, take a break. Okay, everyone, welcome to go back here. For the self-purging redundancy method we discussed in the last week, I would like to thank two students who asked some questions so that I can clarify this question to you more clearly. For these methods, there is one limitation. They cannot tolerate two modules simultaneously failing. So here I try to design a negative example for you. So for example, for self-purging redundancy method, we have 5 modules. Let's assume that now the correct answer should be 0. So for example, M1, M2, M3, these 3 modules generate the correct result. It is 0, 0, 0. However, there are 2 failing modules, M4 and 5. Because they are faulty, so the output should be 1. In this case, you will find that because for the threshold voter, its functionality is that if we find the number of inputs that are logic 1, this one is actually logic 1. If the number of inputs that are logic 1 to this voter, then the output will be logic 1. So if focusing on only logic 1 inputs, so in this case, the output of the thresholder will become logic 1. So you will find a very bad result because this voter think these 2 ones are correct. So this one will be used to switch off this one, switch off this one, and also this one. So this is the most serious, the worst case of these methods. These 2 failing modules will be used to turn off the good modules. And the reason is that we design the threshold voter functionality like this one. We only care about the number of input that are logic 1. So you can draw this, you can put this example in this slide so that maybe you can more understand the ideas. However, think about the other example. If the correct result is 1, 1, 1, is 1 in this one, then even though these 2 generate the faulty output as 0, in these green examples, the threshold voters will still generate the correct result because there are 3 ones here. That is larger than the threshold. In this threshold voter, the number is 2. So for this case, because we have 3 logic 1s, so in this one, the correct result should be still 1, and it will be used to switch off this one and this one. Okay, so the risk is in this blue one and the red one case. So that is why we say it cannot tolerate 2 modules simultaneously failing. So maybe using this case, you can think, if you are the designer, do you have any solutions that can avoid this risk? So maybe you will need to solve that problems for your future research or your future products for your IC design companies you joined. So here, yeah, I hope this can be helpful for you to understand why we say it cannot tolerate 2 modules simultaneously failing. Yeah. Okay, so you can think about that, and you can let me know if there are still some questions. For this time redundancy methods, now let's try to see some specific examples how we can use time redundancy to detect if there are any errors. Let's talk about rollback for this one to have more some specific information. Because in order to do the rollback, we need to save these non-good states so that we can, when we find errors, we can go back to these non-good states to make sure our system can still have good results. So it means that we need to add some storage to state the previous states. Okay, and the amount of the rollback, how many times you want to do this rollback, is actually depending on how much latency of the error detecting mechanism your methods have. So let's assume that your latency is very little, Then, in order to maintain the original system performance, then there are some limitation of the amount of the rollback. So every time you do the rollback, you will have some time penalties. Okay, so if you can try to reduce the latency of error detecting mechanism, for example, you only want 0.01 nanosecond to do the error detecting, then within one clock cycle, you will have more flexibility to do the rollback. Maybe you can do multiple times. Okay, so usually if we want to use time redundancy methods, we want this one, zero latency error detecting, which means that the errors can be detected in the same cycle when the errors occur. So zero latency means that we can, when you do some computation in some certain cycle, in that cycle we also detect the errors. So we don't affect the number of clock cycles you have. So if we can do that, then we can, in the same cycle, also do the rollback. So this is I think the ideal case if we can implement this one. So for some methods, you will find that their goal, their objective is to implement zero latency. Okay, so this property is very important in order to minimize the time penalty, performance degradation of our methods. So rollback here, if we do the rollback, actually we want to prevent the system state from updating. If we can detect the errors in the same cycle, then when we do rollback, we can prevent the system state to be updated because we do that in the same cycle. The system state should be updated in the next one cycle. And because we detect the errors in the same cycle, we can prevent the system from updating, so the system can still use the same correct way to do the computation. So this is also one purpose or advantage of this zero latency error detecting. So you may think that for your research, maybe your solution also needs this zero latency. Maybe even though your problems for the research is not the same here, but you can still think if zero latency, if required or having some advantages of your thesis study. However, you can think that if errors detected after some other cycles, for example, your method is not so good, your error detecting methods need to detect the errors after a total of n cycles, which means that you know your system is wrong, but after n cycles, then when you do the rollback, you need to restore the system to the state at least n clock cycle earlier. So which means that these n cycles are wasted because you know the errors very lately. So if you want to make sure the system is still good, then you need to roll back so many clock cycles. So your system performance will be very seriously degraded. So this again shows you zero latency error detection is a very good advantage that we can try to achieve. So this is about rollback. When we do this rollback, we say that we need to add some storage to save the previous state. This previous state, we can say it as a checkpoint, 检查点. Okay, so I'm not so sure for your PC, do you usually store checkpoints for your PC? For Windows? Personally, I don't do that because I think it is too troublesome. Yeah, but for Mac, how about Mac? For the Mac, if you use Mac, do you store these good states often? But you are, maybe that means that you don't worry about crash of your system, right? How about, what do you do if you find your PC is crashing? Just accept it. Maybe you will say that is that is the real life. In our life, we usually have some crash. Do you see the blue screen for your PC often? No. So maybe you will be quite worried if you are doing experiments for your master study. For your master study, you need to perform a lot of experiments. And if you find the operating system is crashing, I think you will also be very crash. Because it means that you may need maybe half of the year to redo the experiment. You need to graduate 0.5 years later. So it will be very, very serious. Yeah. So usually, if we need to have our system very reliable, we need to establish checkpoints so that we can, at least when we find there are some errors, we can go to that checkpoint to restoring the states that are correct. So I also encourage you to do that for your experiments for maybe undergraduate projects or the master study. Try to establish some checkpoints so that you can make sure, even though there are some errors, you don't need to do it totally again. Okay, so this is checkpoint. If there are any errors, then it is quite easy to understand. We go back to the last one checkpoint and retry operation. And if there are multiple tries, but you don't see it is successful, then it means that your system has a very serious permanent faults. So you need to hold the system and try to do some repair. So that is the idea of the checkpoints. Okay. So how can we specifically implement the time-based check methods? So the first one, repeated execution. So for example, we repeat the operation twice. Okay, so it is the simplest time redundancy methods. We just need to control our system. Every time you do the operations, you do it twice. So you can easily imagine that this one is the simplest method. However, its performance cost is very high. Okay, so for this one, again, it detects temporary faults occurring during one execution. It cannot detect the faults that affecting both the two executions. Okay, so the advantage is that we can reuse the same hardware for both executions. So actually, you don't need to add any cost of the hardware. You just need to pay the cost to repeat this operation twice. So this is again a trade-off. Okay, so you can, for this method, we need to have some mechanism to store and compare results of both executions. Okay, so in order to solve this one, in CPU, we can store this good result, the checkpoints, in the memory or disk and use software to compare. So again, it shows that we don't need additional hardware. We just need to use some software and some memory storage. This is our cost. Okay, additional time. Okay, so when you learn these techniques, focusing on what cost we need to pay and what advantages we can have. We can have the other way to check, to do the compare results of both executions. We can use the multiple threads of the current CPUs. In your CPU, you will easily find that it supports multiple threading. So actually, we can use multiple threads to do this one, to implement this one, operational twice. So multiple thread is basically a parallel processing methods. So actually, you can do the operation at the same time if you put this operation in different threads. So we don't need to, so these two threads can be executed at the same time. You can use this way to reduce additional time you need. So that is for these multiple threads. So if you are familiar with this one, you can use this solution to minimize the time cost you need to pay for this redundant execution. So this involves with 2 copies of the thread executed. The keyword here is concurrently. Okay, this one. So this is a easy idea that if you think your time penalty, time cost is too much, maybe you can consider try to use some parallel processing, 平行处理. So you can use threads in CPU that is already existing for you. Okay, so we take advantage of CPU's built-in this one threads capability to do this one. So we can reduce execution time, significantly reduce performance penalty. So yeah, I hope that if in the future you find you have some cost problems related to time, maybe you can think about this thread or parallel processing to be part of your solutions. Okay, let's talk about some circuit level implementation. If we want to check for some hardware module output, if the output is correct or not, how can we implement the time redundancy based methods? So now I will introduce you the circuit level one example of circuit level implementation. The idea is also very simple, but we need to think about how can we implement this idea. The idea is that every time when we compute the output of the module, we do it the second time and sample the output after a delay of delta t. So this is the original function you are familiar with. Every clock cycle after positive clock transition, you can compute the output of the module. However, we will do it again after delay of delta t. So of course, we want to minimize this delta t so that the timing cost can be minimized. And we compare these two samples to see if there are any errors. So here, one key point is that depending on the value of your delta t, it determines what kind of faults you can detect. For these methods, we can detect any temporary faults whose duration is less than delta t, which means that when you have normal clock cycle, you have some results. If there are some temporary faults, it will affect your output, but the duration, the length of the clock, the time that affect your output is less than delta t. Then you will find after delay of delta t, you sample the output again, you will find some different results. So that is its limitation. You will find that it is an interesting trade-off. If you have larger delta t, then you can claim that you can detect more temporary faults because the duration can be larger. However, if you increase this delay of delta t, it will also slow down your performance of the system because you need to output the results after this delay. So it means that you cannot output this result to the other module just after clock cycle. You need to wait for additional delta t time. Okay, so that is a trade-off. You need to evaluate and determine what is the best value of delta t for your result. So actually you will find that in your master study, it is quite common that you need to answer one question. What is the best value of your solution? So it usually is associated with some trade-off. So here we also have this trade-off. We want to detect more temporary fault, but we also are concerned with the performance overhead. So here, performance overhead is very important. There are some trade-off. Okay. This is one simple approach that we can implement this sentence. How can we sample the circuit output again after a delay of delta t? This is one example. This is your original flip-flop. We just need another set of flip-flop. We call it shadow latch. So shadow means, in Chinese, it is 影子. So basically, it is a copy exactly the same as your original one. So this is a shadow latch. You can see that this signal is our circuit output. So originally, you sample this circuit output every, for example, positive clock transition. Now you need to sample this one again, but you see here clock is a little bit delayed by delta t. And then we have a comparator in the end of this system to compare if there are any differences. So this is one possible scheme that you can try to implement in your design if you think this approach is the best for you. So we can use this way to detect if there are any errors. If we find any errors, then this error signal can be used to trigger your system to do the here rollback, to do this one rollback mechanism. Okay, so try to link this concept together. If we have this circuit implementation in your design, then you can know if there are any errors in your operations. If we find any errors, then this error signal can be an enable signal to trigger your system to do rollback. Okay, so this is one. This is the multiple sampling methods. So if in the future you need a circuitry to do multiple sampling, maybe you can go back to this slide to use this scheme. Okay, so this is one example. It's this one. It is called by stability checker. You can try to understand the ideas here. What is the stability checker? It is basically this circuitry. And again, we have a normal clock period for your original design, but we have a delta t. We call it by stability checking period. Okay, so after your normal operation, we need additional time, delta t, to check if this output is stable or not because of some temporary faults. So let me show you some example of this one so that you can know the functionality of this one. So let's put some numbers here. If we say that there are some output circuit output goes to this stability checker, and now we are in this normal clock period. So this checking period is 0. We don't enable this checking process. Then you will find that there must be no errors because of this 0 here. And then if we in this stage, we want to check this output, if this output is stable or not, then we enable this checking period to 1. And you will find that if we enable this to 1, if there is no transition in your circuit output, which means that we don't have temporary faults, then even though we have some transitions here, the output is still at 0. However, if in this period your circuit output is not stable because of some temporary faults, then this may have some transitions here. For example, from 1 to 0, then you will find this error will become 1. So this is one stability checker. If you think there are some component in your system, you are quite care about its output stability. So for example, maybe this is a controlling circuit for your CPU. You need to make sure this control output to be very, very stable. Then maybe you can put this stability checker in the end of this module. So you can use this way to check every clock cycle. You need additional delta t time to check if this is good or not. Okay, so this is one. Okay, so this is the other way that we can check the stability of our outputs. Okay, so this is the example here. Finally, I would like to give you another idea. It is somehow very different from the claim we talked to you for time-based redundancy. For time redundancy based, actually we said that it cannot be used to detect permanent faults, right? We can detect temporary faults, but time-based redundancy cannot detect permanent faults. Do you think this is right always? do you have any solution that you may think it is possible that time-based redundancy may also detect permanent faults? Actually, it is possible if we try to use this one, diverse recomputation. The idea is that for time-based redundancy, actually we always assume if we want to repeat the operation is exactly the same. That is our assumption. We want to do the same operation so that we can very easily do the operation. However, if we try to relax this assumption, so for example, let's consider diverse recomputation, then you have the possibility to detect permanent faults. So the idea is that the hardware is the same. However, we try to shift the operand. We try to modify the inputs. We redo the execution. So here you can see that we perform computation differently second time. So here, the keyword here. In our previous slides, we all assume if we want to do the operation second time, the computation is exactly the same. That is why we cannot detect permanent faults. However, if we allowed the system to perform computation differently second time, then it becomes possible we can detect some permanent faults. Okay, so for example, how we can do that? For arithmetic or logic operations, we can try to shift the operands. So for example, in the current operation, you want to do some addition, 加法. You want to sum up the inputs together. So for example, in the zeros bits, originally you sum up the zeros bits of the two inputs. Next time, when you retry this operation, you shift the input so that, for example, it is the same hardware to calculate the addition, but now you calculate the first one bit of the data inputs. So basically, idea is like this one. Let's assume that this is an adder, and for this one, this is the zeros 4 adder. So basically, for this zeros 4 adder, you will calculate the sum and carry out. So usually, when we use this adder, we should put, for example, A0, B0 here, and this first one bits A1, B1 bits. So, for example, for this diverse recomputation, at the first time you use this A0, B0 to calculate sum and output. But next time when you do the operation second time, you shift this input so that you use A1, B1 to the zeros 4 adder to calculate sum and the C out. So in this way, if there are some permanent faults that will affect this zeros 4 adder, we also have some circuitry. If there are some permanent fault here, because now your first time you use A0, B0, second time of the operation you use A1, B1, so the input is changed. If there are some permanent faults in this zeros 4 adder, then we can detect the permanent fault affecting only 1 bit slice. This 1 bit slice, you can think that as this one, some bits of the 4 adder. So the key part is that because we try to use different inputs, so we can find that, for example, if this is 0, 0, then maybe 0 output should be 0, right? And if there are some stuck at 1 fault, to have some as 1. If A1, B1 is 0, 1, then you will find that we have two different inputs, 0, 0 and 0, 1, but the output is still 1. some output is still 1, then we can find there are maybe some permanent faults here. So that is why we say that. So it is possible that we can make our time-based methods to detect permanent fault, but we need to do diverse recomputation. And we need to do additional maybe modification of the hardware such that we can shift the input to this hardware so that we can compare if there are any permanent fault here. So it is this one. If we do that, then it is possible we can detect the permanent faults. So I just want to let you know that it is possible we can try to make our time redundancy method to detect permanent faults. But we need to do the recomputation differently. Okay, so try to see it and to see if you understand the concept. Okay, so this is for this one. So this is for time redundancy based methods. Okay, and we introduced several time redundancy based methods. So you can also think about if you are the designer, which one should you use and the cost. Okay. Finally, it is the information redundancy. So it is basically that we want to put some additional bits in our signals. Originally, for example, we have our circuit output, for example, 32 bits. If we try to add more bits in our signals, maybe we can detect the errors and also correct the errors. So this is information redundancy. For this one, because actually there are a lot of mathematical theories and models. So later I will just focusing on some important concept and some examples to let you know the critical parts of this information redundancy. Basically, it is error detecting and correcting code. I'm not sure if you heard error detecting and correcting code before, ECC. Have you ever heard that in your communication system course? 通讯理论. Do you hear that in that course? How many of you hear error detecting and correcting code? If you hear that, please raise your hand. No? No one? No one heard ECC? No? Okay. So yeah, maybe it is good for our course. At least I can let you know the ideas of ECC. Because ECC is very widely used in our memories. And now you know the memory is very expensive, right? It is even more expensive if you buy memories with ECC, error correcting code. When should we use ECC embedded memory? In which scenario you would like to pay more money to buy ECC enabled memories? 伺服器, server, right? So I think maybe you will not buy it. Your advisor will buy it for you, because we hope the experiment to be done very reliably. So this one ECC, is very widely used in memory. Maybe you can try to Google that. If you buy memory with this capability, the cost is very high. But you can get the advantage. You can make sure your memory data is very reliable. We can use ECC to detect the errors. If there are any errors in your memories, and then try to correct, try to make the errors disappear. So ECC includes the two parts. The first one is error detection, and the second one is correction. And ECC usually error correcting So I think it is worthy for you through this course to know ECC a little bit more, because maybe it will become one of your solutions for your research, error correcting code. Okay, so actually it has a lot of applications for ECC, especially combined with memory. Actually, we also have some examples for ECC to combine with logic. ECC can also be combined with logic. If you are interested, you can try to Google this one. It is not only be applicable to memories. We can also do that for your logic circuit. Okay. So the advantage, we can detect both permanent and temporary faults. And its hardware cost is less than that for hardware redundancy-based methods. We just need to, for these ECC methods, our hardware is used to encode your information and decode. So later, for ECC, we will need to care about how to encode your signal and how to decode your signal. Okay, so pay attention to these two ideas later. Every time when we want to check your signal is correct or not, we need to add some more bits into your data. That is the encode. And then when we read the data, for example, from the memory, we decode, try to check if there are any errors in your memory data. So later we have these two ideas. But actually, because we have limited time, I don't want to let you feel quite confused. So later, actually, for this ECC, there is a lot of mathematical equations and matrix computations. If you are interested, you can Google that, or even use AI tools to help you understand ECC theory. So later I will not do that. I leave them for you to do that if you are interested after the class. So later you can put your attention into encode and decode. For encode, we add more bits into your signals, and then during decode process, we use those additional bits to check if there are any errors in your data, and then also do the correction. So that is the powerfulness of this method. We can detect the errors, we can also correct the errors, but actually there are also some limitations. Later we will see that. Okay, and so its hardware overhead will be less than that for hardware redundancy method. For this ECC, we don't directly copy the whole module. We just add more bits to your signals. So the hardware overhead will be this, than that for hardware redundancy methods. And it will make our circuits to become more complicated because we need to do the encoding and the decoding. So if you try to Google that, you will find some IC designs for ECC encoding and the decoding. So maybe that is maybe one possible topic for your master research. Okay, so here, error detecting code used to detect the errors very obviously to detect. So again, if error is detected, then we roll back to the previous known error-free state retry operation. Exactly the same for time redundancy-based methods. So that is the benefits if we can detect the errors using error detecting code, or this one, ECC. They belong to the same category. So here is one example, how we can add more bits to detect the errors. So this is our input to our original functional logic, and usually we will have another circuitry. It is this one. It is used to generate some additional bits. We call it by check bits. So it is very logical. We need to have some more bits. This, for example, this original K is 32 bits. for your CPU. But now we need additional C bits, for example, 4 or 5 bits, to serve as the check bits. We use this check bit to check if there are any errors in your functional outputs. So we have a checker here. So for ECC, you will find that the architecture is usually like this one. We have these inputs. In addition to the functional logic, this input also goes to check bit generator to generate some check bit and try to use this check bit to check if there are any errors in your functional outputs. If yes, then this error signal will be 1. Otherwise, it is 0. So this is the very basic idea. We need to generate this check bit to check that. So the question is that, how can we generate this check bit, and how these check bits are used to check the correctness of this functional logic? The very fundamental example of this check bit is this one, single bit parity code. This is one very representative example of check bits parity code. So keep this one in your mind. Parity code. You will easily find parity code in many papers or even some memory product parity check. And let me ask you one question first. Have you ever heard parity code or parity? What is parity? In Chinese, it is 即兴, but I don't think it is helpful to let you know the Chinese for this word. Parity. What is parity? I think you should learn that in your first year of your university in digital system design. Do you remember that? Parity. What is parity? What is the parity of a signal? For example, this one, 1, 2, 3, 4, 6 bits. What is the parity of these 6 bits functional outputs? Anyone who want to try? Yeah. Just say anything you remember about parity.
Even or odd number.
Yeah, even or odd. Can you explain that more? What do you mean by odd or even?
Like the first bit of the number is 1 or is it 0? Yes.
Okay, quite close, but it is great that you mentioned odd or even. Okay, your name? Let's give a big hand to Binqi to mention. Yeah, very good. Even or odd? When you hear even or odd, do you have any ideas?
We will decide the number of 1 or number of 0 is even or odd.
Yeah, very great. The name? Li Heng. Let's give Li Heng for this adding information. Yeah, very great. So parity is the number of ones or zeros. Depending on how you decide the parity, you can determine it. So for example, let's define parity as number of ones. For your outputs. If the number of ones in your output is odd, then its parity is called by odd parity. And on the other hand, if the number of ones is even, then the parity is even. Look at this example. What is the parity of this output based on our definition? For this one, it should be, we have 3 ones, right? So its parity is odd. However, now for this parity prediction, for this one, it is used to generate a specific 1 bit. For this parity prediction, remember that it is 1 bit parity bits. For this one, the purpose is that no matter the output of your functional logic, if we have this output together with this parity bits, we can always know your output parity should be odd or even. That is the parity predictions purpose. So for example, if your functional logic is 0, 0, 1, 0, 1, 1, its parity is odd, then our parity bit is 0. So the 1, 2, 3, 4, 5, 6, 7, the 7 bits information is always odd parity. Let's talk about the other one example. If now your functional output is 0, 1, 1, 0, 1, 1, how about your parity? If now your functional output is 0, 1, 1, 0, 1, 1, because you see now the number of 1 should be even, right? So the parity bit will generate 1. So that this one, again, its parity is always odd. So the parity bits, actually, it is used to make sure if your functional output is correct, its parity should be consistent. It is always odd, for example, here. Then that is our purpose. We want to know if the circuit output is correct. Can we say its parity is always odd? So we use this parity bit to help us to say that. So in this case, these 7 bits outputs, we say it is the parity should be always odd. Then we can use this property to check if there are any errors in the functional logic. For example, if there are some errors inside your functional logic to make this bit to flip from 0 to 1, then you will find that its parity changed from originally this 1 parity is odd, it changed to even. Then we can know there are errors. So remember that the correct output, we use this parity output bits, 1 bit, to make sure your correct output should always have the odd parity in this example. So if there are any errors that changes your output, it may be possible that the parity will be changed. In this example, it will become even parity. So we design a checker to check if there are any parity changing behavior for your output. So this is a typical parity checker design based on some exclusive OR gate. If you see this one, it is an exclusive OR gate. And we usually connect it to a hierarchical design. So we call it XOR tree. So, but that is too technical. Just let you know we have a checker to do that. So usually checker is implemented by exclusive OR tree. So this one corresponds to this one, checker design. And the check bit generator, it is actually this one. Basically, it is also an XOR tree. You can think about that. How can you generate this parity bit? How, if you are the designer, how would you implement this parity prediction circuitry? Basically, it is you can use exclusive OR gates to deal with this output. Then you can generate the parity bits. Okay, so this is the idea. Okay, and here one more details for you. When we design this checkers, we usually design it as the totally self-checking checkers. This is a specific keywords. If you are interested, I encourage you to Google this one. For this one, it is actually this circuitry. There are 2 purposes of this totally self-checking checker. The first one, purpose, to check if there are any parity changing behavior because of, for example, this blue one is an error. if the output is the parity is correct, this checker output will be, for example, 1 0. However, if there are some errors for the functional output, it will generate some output result to become 0 0. Then you know there are some errors. This is the first one purpose of this one, to check if there are any modification of the parity because of these errors. The second one thing, how do you know this checker is correct? That is a very important question. Maybe for your oral defense of your master study, you design a checker to check if this is correct. Then your oral defense committee member asks you, how do you know this checker is correct? How do you respond that? That is important question, right? If this checker also contains some errors, how can you guarantee this output can be reliable? So very important. But you cannot say to your oral defense member, I don't know, I just assume it is correct. Then he or she may tell you, I also assume you cannot pass. How can we do that? So totally self-checking checker has another one very property. If there are any faults inside this totally self-checker, then the output will not be 1 0 or 0 0. It will become 1 1 or 0 1. So for this totally self-checker, it will have a legal code word. We will say that legal, 合法的 code word. It means that if we have the correct behavior for the checker, the output should have some format. So for example, its output maybe only 1 0 or because of some errors become 0 0. However, if there are some, for example, start 1 fault in the output here, then this 0 will become 1. So for this example, legal code words for the output should be 1 0 or 0 0. However, if there are some faults inside the checker, it will become, for example, 1 1 or 0 1. This is illegal code word. So we can use this legal or illegal to check the format to make sure if there are any faults inside the checker. We will determine if your functional logic is correct or not by first checking the format of your output code word to see if it's legal or illegal. If it is illegal, then we say your checker is faulty. For example, if you find the output is 1 1 or 0 1, that means that your checker is faulty. If the code word is legal, then we check it is 1 0 or 0 0 to determine if your functional logic is correct or not. So that is the idea of this one. Totally self-checking checkers. If you design some checkers to check the other one, you need to make sure your checker is correct. You need to know if your checker is good or not. Then you can use this technique, totally self-checking checker. Okay, so that is the idea. Okay, so this is one very famous idea of single bit parity code. And if we have this parity bits, we say, remember for this one, encode. What is the encode process of this mechanism? The encode mechanism is 0 0 1 0 1 1, the functional output, plus this parity output. So when we do the encode, we generate these parity bits. And how about decode? We use this checker to do the decode process to let us know if there are any outputs that can indicate if there are any errors in the outputs. Okay, so encode, decode. Okay, so here encode means that we will add some more information to your original output. Decode means that we will use these parity bits to check if there are any errors and even correction. Let me ask you one question before we have break. Can this parity code used to correct your output? If you see this example, can we use this parity bit to correct your output? In this case, we know for these parity bits, we know there are some errors for the output because the parity is changed. But can we do that? Can we use this parity code to correct your output? No, very difficult. Impossible. We can just know there are some errors, but we don't know where is the location, right? Because if you have this 0, 0, the errors may come from this 1, or this 1 become 0, or this 0 become 1, as long as only one bit is flipping. So there are many possibilities. We don't know which one is your error case. So we cannot correct using parity code. So usually parity code is used to detect errors only. If we want to correct your output, we need another powerful ECC code. What is another powerful ECC code? Later you will find out we will need more check bits. If you only have one check bit, you can only detect errors. But if you can have more check bits, then it is possible you can correct the errors. So how many bits you will need determines your cost, right? Because originally you just need 6 bits in your system. When you write arterial code, you only need 6-bit output. Now you need 7 bits, so you will have more interconnection. This is important, especially if you have the experience of the APR, the layout. If the interconnection becomes more complicated, your layout will become also complicated. Then when you tap out IC, maybe it will make you need to pay. Some of you tap out the IC. Do you pay the money so far? No. I believe you don't need to pay because your area is restricted to some values. But if you have more bits, you will have more interconnect. Your area will become larger. Okay. So later we will put focusing on, can we try to add some more check bits so that we can do the error detection and also correction. Okay. So let's take a 10 minutes break. Please come back before 11:19. Okay, so now we have about 25 minutes. So in the final 25 minutes, I just want to let you have some ideas about how can we have more check bits so that we can detect the errors and also correct the errors. Before that, let me give you one idea. For this original information, for example, this 6 bits, if we have additional 1 check bit, then this 7 bits information, we call it by code word. So because this process is encoding process, so now we should have these keywords. After encoding the information, we call it by code word. So this code word will have legal and illegal. So we use this legal and illegal to differentiate if there are some errors. Okay. Okay, so for the single bit parity codes, there is one limitation here. Just let you know, and you should be able to easily imagine that it cannot detect even bit errors, because if you have even bit errors, the parity actually doesn't change. So for example, if you have this 0, 1, 0, if this is also error, there are also errors here, then it will become 0, 1, 0, 0, 1, 1. Its parity is still odd. Then this checker will report there is no parity changing. You will think there is no error. However, in this case, there are 2 errors. So it cannot, this is the limitation, it cannot tolerate even bit errors originally. However, this is one exception. Maybe we don't have time to explain that, but the idea is that how can we, if it is possible that we can modify our circuit structure so that we can still use this single bit parity code to check if there are any errors, even though multiple even bit errors. The idea is that we need to modify our circuit such that if there are any errors, it must affect only 1 bit of your output. So the idea is just like this one. Maybe I can draw a figure for you to let you know that. This is our circuits, and here is input, this is output, and this is maybe output 1, output 2. Okay. Let me check. Okay. When you design the circuits, usually your output will not be driven by only 1 gate. So, for example, this output, if we try to trace which logic gate determines the values of this output, we may find a range. This range is called by cone. If you are interested, you may keep it in your mind, because this is a terminology we usually use for circuit analysis. So usually for this one, there may be some multiple input and multiple logic gates. So for example, this may be some logic gates. This cone means that the inputs and the circuitry that will determine this output. So we can draw this one, and usually we will find that there may be multiple cones that will determine your output. This is cone 1, and this is cone 2. So it means that we will have some sharing of these cones that can determine your outputs. Because the single bit parity code cannot detect even bit errors, so if we want to use single bit parity code to apply to our circuit and make sure every fault we can detect, then what we want to do is that can we try to modify our design such that we can satisfy this property. So this is the conclusion. Maybe you can focus on this sentence, and I will give you how can we do that. If there are only single point faults, we need to make sure only single bit errors will occur. If you have this, maybe let me rejoin this one. This cone will determine output 1, and maybe this is another cone 2. This cone will determine output 2, but here you will find that there is some overlap. This overlap is called by sharing. This logic gate will be shared by output 1 and output 2. So if there are any faults, for example F1 here, this fault will simultaneously affect output 1 and output 2. If this fault occurs, then single bit parity code cannot detect, because this one may make output 1 and output 2 to change its value. However, we can try to redesign this circuitry such that for each output, O1 and O2, the logic gate will not be shared by different output, which means that for each output of the circuit, we only have one cone to determine its output. These two cones will not have any overlap. If we have this structure, then we can make sure if there are any faults here, it only affects one output. So if we redesign our circuitry such that we can have this property, then we can use this single bit parity check to check if there are any faults in your design. However, I need to tell you that you can do that. You can think about how can we do that. I just want to let you know that if we do this one, then your area and the interconnect will become very high, because originally you can share some logic gates to determine the output. So that is the idea in your maybe digital IC design. You want to reuse the hardware as much as possible to reduce the area. However, now if we change our circuitry like this one, it means that there is no reuse of your hardware. Every hardware only responsible for only one output. There are no sharing in your design. Then you will find this area maybe 2 times larger than this one. So this is the cost. You need to increase area in order to satisfy this property. If you have this property, then you can use single bit parity check to detect if there are any errors. However, you need to pay a lot of cost. So if you are interested, you may think about that. This is your original design. You share some hardware. How can you redesign your circuit such that no hardware sharing in your design? Okay, so this is the idea here. So if we try to modify our circuitry, then this single bit parity code may be useful. However, because this cost is very high, so usually we will not do that because a lot of overhead. Yeah. Okay. The other one is duplicate and compare. This is exactly the same as we learned before. We have one functional logic. This is exactly the same, the same copy of our original one. So you can think this one is used to generate the check bits. So this is the check bit generator. Maybe you can take some notes. We use the same original one as the check bit generator. Then we compare if these two results are the same or not. This is the equality checker. If you do it, then you will find that no matter how many bits you have errors, this equality checker can detect the errors. So if you do that, then we don't have this limitation. Even though for this circuitry, even though we have multiple even bits of the errors, this equality checker can find the errors. However, you will find that one cost, you need 100% of the hardware cost, because you use the same functional logic to implement the parity bit, the check bit generator. The second one, only faults after stem are detected, which stem is this one. This is stem. Pay attention to this bold break point. This is stem. Only faults after this stem can be detected, because if you find there are some errors in here, it will affect this one and this one at the same time. So your output may also be the same. It will make the error undetectable. So for this scheme, the limitation is only errors are occurring here, here, here. Then it affects only this one or this one, so we can detect the errors. So it is the limitation. Okay, but the advantage is that we don't have this limitation. We don't have this drawback. For this scheme, all the numbers of the errors can be detected. Okay, but its overhead over 100%. So it depends on, do you want to have this trade-off in order to release this limitation? You need to pay 100% overhead. Finally is this one, error correction. Okay, so for this error correction codes, the idea is that we will need more check bits in order to not only detect the errors but also correct the errors. Okay, so for this ECC methods, this is called by ECC. It is commonly used for memories. So in addition to the memory data, we will also generate check bits and store them in the memories. Okay, so later you will see that for this ECC, there is one representative ECC method called by SECDED. So this is one keyword that you can keep in your mind. SEC means single error correction. DED means double error detection. So which means that for these ECC methods, we can detect at most 2 errors. And SEC means single error correcting, which means we can correct only 1 bit errors. Okay, so later you will see this one again. Okay, so this one, single error correcting, double error detection. So it means that for this code, we can only detect up to 2 errors in your stored data, but we can only correct 1 single error. So it means that if for your memory data there is only 1 error, then this error can be detected and also corrected. However, if your memory data contains 2 bits errors, then this error can still be detected, but it cannot be corrected. So here you need to know that for every ECC bit, it has some limitations depending on how many checking bits you have. If you only have 1 check bit, then you can only have this one, single error if you only have 1 bit, then it should be this one. If you only have 1 check bit, then you can only detect the odd even number of errors. If you can allow to have more check bits, then you can have this one, single error correction. If you have more check bits, then you can have single error correction and a double error detection. So here the idea is that if you can have more check bits, then you will have more capabilities. But the cost is that you will need more bits to be stored. That is your cost. So later you will find that for every different methods, what we care about is the first one, how many bits errors you can detect and correct. Second one, then how many bits, additional bits, you will need to store into your memories. Okay, so that is the two concerns we will have. And there are actually many types of the ECC code. If you are interested, you can look up this textbook or just Google or use AI tools to realize or understand the ideas of different code here. Here I just want to give you some idea. For example, for this one, how can we generate the check bits, and how can we use this check bit to detect errors and correct errors? Later I will give you some examples and to do some exercise. Okay, so error correction codes are very widely used to memories because memories are very dense. Their density is very high, so they are easy to be affected by single event upsets from radiation, which means that some radiation, some alpha particle will, when they hit the memories, our memory bits will have some bits flipping from 0 to 1 or 1 to 0. So you can imagine that because for memory chip, the transistors are collected very densely. So any alpha particle from the space, when they hit our memories, it will charge or discharge our memories. So it is very possible that this radiation will cause this single event upset. SEU is also a very commonly used terms for the reliability, which means that you can see that single event. Single event means only one bit of our memory will be affected, and it will cause upset. Upset means from 0 to 1 or 1 to 0. So we hope our memory can have some capability to detect the errors and correct the error. And because this radiation usually have single event upset, which means only one bit will have errors. So if we have SECDED, then this error must be detected, and even this error can be corrected. So that is the reason why when you buy memories, you can find there is an option for you. Do you want to have this ECC capability for your memory? If you buy it, then you don't need to worry about this radiation soft errors. This is actually the soft errors we introduced in the beginning of our slides. Soft errors because of the radiation. Yeah, so that is the applications. And here one important concept is that it will need to have more check bits and embedded into your memories. So here you can see that if we have 32 bits word, this is your original signal with 32 bits. Then if you want to apply SECDED, you will need 7 additional check bits. If you have the memory with 64 bits, then you will need 8 check bits. The importance of this information here is that it will increase the size of your memory. Originally, you just need to store 32-bit words. However, in order to get this benefit, you want to correct single-bit error, detect double errors. You will need every 32-bit words, you will need additional 7 check bits. So it will increase the memory size. So here you can see for different memory specification, you will need this cost. So this is why we say if we allow more check bits, then we can have these capabilities. Okay, so this is for ECC. Okay, so for this part, because maybe we don't have enough time to go through every part, so maybe I just let you know. For coding, they use more bits than necessary to represent data. This means that originally we need 32. Now we need 39 for every information. So more bits than necessary to detect the errors and then to to correct the errors. Okay. So here, maybe I can just skip these slides because they are quite mathematical. I don't think you are interested in these mathematical equations. But I just want to let you know this redundancy. For every error correcting code, we need to care about how much redundancy we need to have. So you can see that if you have the m messages, and now you use n bit code word to represent it. If you have m messages, for example, 64, for example, we have 64 possible types of the information. What is the minimum bits we can represent this 64 information? What is the minimum bits to represent 64 information? 6, right? Okay, so this is log 2 of this m. This is the ideal minimum width, and n is the final information bit you use. So for example, this is the minimum 32, but in order to have these 7 check bits, your width need to be increased to 39. So usually if you try to look up some ECC code, you will always find there is redundancy information. Try to calculate for this error correcting code how many redundancy you need. Okay. So okay. And for ECC code, there is one idea that you can have in your mind. If we have n bits to represent our information, then it is very easy to understand. We will have 2 to the power of n information. Then this 2 to the power n information can classify into code words and non-code words. Remember that after ECC, if your information is correct, then after error after the encoding process, your correct output will become legal code word. It's this one, legal code word. If there are any errors in your memories, for our ECC, it will become non-code words. So the idea is that if there are any errors that will make your output from code word to become non-code word, then such errors can be detected. So that is why we may need to increase n, because we hope that by increase n, we can divide the information into 2 parts. The one part is the legal one, code words. If your output is correct, then after encoding by ECC, for example, plus the parity codes, then it will become legal code word. If there are some errors, then these errors will make your output to have non-code word. Okay, so that is the idea. So later we will use example for you. How can we generate the check bits, and then we use those check bits to check if the output is code word or non-code word, and then you will find that non-code words cannot, if the output makes the code word to become non-code words, then such the errors can be detected. Okay, so I leave these slides for you to reference because there are some mathematical one. Let's just begin to this part. Okay. For the parity, for the check bit generator, later you will find we have this one, parity check matrix. So for every code word C, this is the information including your original information and the check bits. If this information is correct, then it is a code word. Then when we multiply this code word with this parity check matrix, then it must be 0. So this is what we need to use to check if the output is error or not. So just keep this in mind. Don't worry, later I will give you an example to let you know how can we use that. So this, keep in your mind that for ECC, we use a matrix to check if your data in the memory is good or not. If your data is good, then when we multiply your data with this parity check matrix, it must be 0. So we will find that if the multiplication is not 0, then we try to find if there must be some errors in your data. And we want to find which part of your data is erroneously. So keep this one in mind. And we also have the other matrix, 矩阵 generator. We use this one, G, to generate the code word. So M is your original data. It will be multiplied by G, then you will generate a code word. Okay, so let me give you some example here. This is the generator matrix. Let's assume that you have 3 bits output of your circuitry. Then this 3-bit output will multiply by this generator to generate a code word. And for this generator, the parity check, the check matrix is like this one. So later, for that example, we will multiply the output with this parity check matrix to see if it is 0 or not. Remember this again. If your output is good, then when we multiply it with this parity check matrix, it must be 0. Keep this in your mind. Okay, let's jump to this one. Okay. Okay, now for this Hamming code, we have the parity check matrix like this one. Then, okay. Then we will do one job to check if there are any errors. Let's assume this V. V is your information stored in the memory. So you will see that V will be multiplied by the H matrix. H matrix is the parity check matrix. If V is code word, then this S must be 0. So this is the correct result. If this one output is not 0, then we say it is non-code word. Then we will try to check what is your 심종, and then try to find if there where is the error. Okay, so let me give you this example for you. Let's assume that this is the code word. After encoding, this is what we stored in our memory, 0110011. Okay, and let's assume that there are some 1-bit error because of the radiation in your memory. So in your memory, this bit happen to become logic 1. So you will have this memory data. We want to check if this memory data is good or not. So what we do is multiply this one with the parity check matrix. This is exactly the same as this one. So we multiply them together, and the important thing is that when you multiply these two together, check if the result is equal to 0 or not. Here you see the result is not 0, right? So it means that there are some errors here. The next one question, can we find where is the error? Basically, when you multiply this one, it is called by 心种. 心种 Chinese is called by 征兆, 病征. Okay, so if you have this 心种, actually it is possible that we can find the error location as long as the bit error is 1 bit. Here you can see that because the 心种 is 001. The next one step, try to map if we can find 001 in this matrix. And you will find this 001 is exactly the same as this matrix row. So it means that because this is the first one row of your matrix, it means it is your first bit to have error. So exactly the same as what we assume. If you only have one single bit error, then you can use this 心种 to find if it is matched to any row of this matrix. The location of the matrix row you matched determines the error location. So you will see that because this 001 is exactly this one, so this is the first one row. it means the first 1 bit is erroneously. So because the memory data is quite simple, either 0 or 1. If this is wrong, then we just flip the result, so we get the correct result. So we just flip this 1 to 0, then we complete the correction process. So let me summarize the procedure again to you so that you can use the next 1 page exercise to do some exercise. This is the memory data you stored in the memory. If we want to check if this is correct or not, we multiply it to the matrix to see if this is 0. If this is not 0, then we say there are some errors here. Then you try to map this syndrome to see if it can be matched to any row of this matrix. If you can find one, then its location means the error location, because this 001 is the first 1 row. So it means that your data, the first 1 bit, should be erroneously. And because this is erroneously, so we just flip this bit to 0. Then you will find this complete error correction. Okay, so just use this example. Try to do the calculation to see if there are two memory data for you. One is this one, the other is this one. There are 2 questions for you. The first one, please try to check if these 2 memory data are correct or not. The second question, based on the calculation result, can you find where is the error location and therefore correct the errors? So these 2 questions for you. Please try to use this example to do that, so that I hope you can have the idea. This is why ECC methods works. Based on the memory data, you will, for every ECC, they will provide you this check-in matrix. So you can do the same thing to check if it is good or not. Okay, so please try to do this exercise and discuss with your team members. Yeah. And later I will let you know the reference answers. Yeah. Try to do the calculation and check if the result is 0 or not. If not, then if it can be mapped to some columns of the check matrix, so that you can determine if the error is can be corrected or not. Yeah. Okay, just another minute. Then I will show you the reference answers and the meanings of these numbers. And then later you can take some pictures. You can complete the derivation after the class, Here the example is I just want to let you have a very basic idea how we can use this memory data with this check matrix to determine if the error can be detected or not. If you are interested in why we can have this procedure, then maybe you can go previous slides. There are some information. You can also check the textbooks or even use AI tools so that you can have a complete story about the coding theory. Okay, so for this tool, if you have this check-in matrix, then we can do the calculation. You will find this is the results. The symptom of the first one memory data should be 0011. And this 0011 will match the S current. So here, 1, 2, 3, 4, 5, 6, 7, 8, 0011. It can be matched. So it means that this error can be detected. How can we correct this error? We find the S bits of the code word 1, 2, 3, 4, 5, 6, 7, 8. This one, originally it is 1, then we correct it to 0. Then this should be our result. And you can double verify this result. If you multiply this 1 to this H matrix, it should be equal to 0. So you will find that because this is a non-code word, so if you multiply this 1 with this 1, it will not 0. It will not 0. And it can be matched. So it is this one. And the second one, the symptom is not 0. So there must be errors. But because it does not match any current, so we can just know there should be 2 bits errors, but we cannot know which 2 bits errors occur. So for this one, we know there are some errors, but it is uncorrectable. So this is some limitation because you only have 3, 4, or 5 check bits. If we can have more check bits, maybe this error can also be corrected. However, because we only have a limited check bits, so we have this limitation. Okay, so when you go back home, please try to calculate this one again. And here you can find the other example. This is 74, which means that we have 4 bits for your original data, but we have 3 bit check bits, so the total number of the bits is 7. If you see this number, which tells you how many bits you have and how many check bits you have. This 4 is the original data bits, and we have 3 bits. And again, if you have this symptom, this data, you multiply by this one, then you will find this symptom is not equal to 0, doesn't match any current, so it is uncorrectable errors. Okay, so finally it is this one. The whole process is that every time when you want to store data to the memory, this data will first to generate the check bits. Then this check bits with this data will be stored in the memory. When you read out the memory data, this check bit will use to generate the symptom, just like we did here. And based on this symptom, we can correct the data if the symptom matches any current of this matrix. So this is the idea. Okay, so here just for your reference. Okay, and finally, it is this table. I encourage you to look at the table here. It just tells you that depending on the applications and your goal, you should select different appropriate methods. So for some applications, we need to maximize MTTF. If the goal is this one, then we should consider this one. If the goal is to high availability, then we can choose this one. So when you go back home, please try to look at this table to let you understand for different types and different goals, then you can select different fault tolerance methods we discussed. This is the industry practice. In industry, we usually use this thinking to determine the appropriate fault tolerance methods. Okay, so yeah, this is just a summary for you. So this is the end of the this unit. So for the ECC part, you can just forget about the mathematical part here because we don't discuss that. So you don't need to prepare for this one. Just make sure you know the ideas of ECC. And if I give you, for example, this one, H matrix and some symptoms, some memory data, you can use the procedure to check if the data is correct or not, and make sure you know how to correct the data. Yeah. Okay, so that's it for our final examinations. Okay, so yeah, thank you for coming for this last one course. I look forward to seeing you again, maybe in the near future. Okay, have a good weekend. Thank you so much. Yeah.